Hi, Florian.
Wonderful. Thank you very much for setting it up. So I myself will start off the presentation on dynamic virtual power plant control, and then Verena will take over when things become more technical. So quick acknowledgements. So Verena, who will give the second part of the talk, she has done the bulk of the work. Also postdoc Michael Fischer and visiting professor Eduardo, both also within POSYTYF. And there was an external collaboration with a few people from Sweden, in particular Joachim Björk from the Swedish TSO, and other people that contributed over time. Outline. So what's on the menu today? I'll quickly present to you the problem, dynamic virtual power plant control. I will abstract it as a model matching problem. And then Verena will take over and talk about how do we actually solve these control problems by means of decentralized optimal control methods, and discuss various extensions and ongoing research. Let's get started. So here's the almost mandatory side comparing conventional and future power systems. As you know, conventional power systems are being run by bulk synchronous generation with a thermal energy source behind. So generation is dispatchable with a significant rotational inertia in the system. And we know very well how to do fast frequency and voltage control. In comparison, future power systems are run by distributed energy resources that are based on variable renewable generation for the most part. Of course, we have reduced inertia levels. And the particular focus today is that the ancillary services are now not anymore provided by a few bulk generators, but they have to be now shouldered by the DERs. Okay, and some of the manifold challenges that I want to focus on, particularly today, are threefold. Namely, there's grid fragility. So the grid is subject to ever more intermittency and disturbances from renewables, and we also have reduced inertia levels. We have device fragility, namely converter interface generation is limited in terms of energy, power, and especially fault current, in the post-fault response. And most importantly for today, ancillary services have to be provided on ever faster timescale for an ever more brittle grid with ever more fragile devices, and now they have to be distributed across many different resources. And this motivates the concept of a dynamic virtual power plant, which is at the heart of the POSYTYF proposal. The idea is, can we coordinate an ensemble of heterogeneous distributed energy resources that collectively should provide the same ancillary services as a single bulk synchronous machine? Okay, and there's a few adjectives in this little proposal that I want to highlight. The first one is heterogeneous. Why do we need heterogeneity? It's because none of these devices by itself is able to provide the same response as a synchronous machine, because maybe they're limited in energy, in power, or they all have only limited bandwidth. Okay, and so you need a collection of heterogeneous devices so that you can reliably provide the service across all power levels and timescales. The second adjective I want to highlight here is dynamic ancillary services. Why is that important? Well, because the grid is ever more fragile, because it ever less inertia, so you need a fast response. And we specify this fast response as a desired input-output dynamic behavior, like a transfer function of these overall aggregation of devices. And we want to be able to implement such ancillary services in a robust way, even though the device themselves might be fragile. And finally, there's the coordination aspect of a DVPP. Namely, we want to find decentralized control solutions, because for the fast ancillary services, we don't think that communication is an option. We want to solve problems really locally as good as we can. And we want to adapt in real time to variable ambient conditions, such as changing grid condition or changing conditions inside the DVPP, for instance, as a shortfall in solar energy production. Some motivating examples. I personally first heard about this concept of a DVPP, or it wasn't called like that, but the overall idea, when I was in Sweden, where the TSO in Sweden discusses that hydro generation should provide fast frequency response nowadays, but it's limited because of its non-minimum phase behavior. Maybe you heard that if you open in a hydro turbine governor system, the gates, the pressure will first fall before the water accelerates. And according to the response has this non-minimum phase behavior, so it will be very poor. And so they thought about augmenting hydro generation with on-site batteries to cover the fast timescales. There's also various proposals about supplementing wind turbines with additional storage, such as a supercap or battery, to cover essential response in all time scales in a robust fashion. More general, there's a concept of hybrid power plants where you combine your favorite notions of, say, PV plus battery plus supercap to provide essentially the same generation or same response as a synchronous machine, and various notions of aggregation of loads and generation. Okay, so it's not completely new, but I should say for all of these different examples, they're custom solutions, and I've never seen it really abstracted as an entire virtual power plant that's possibly also spatially distributed. So let's abstract the problem. The setup is the following. We have a bunch of distributed energy resources that are all connected at a common bus, just like as in this picture. Okay, that's a simplified setup for now. They all get a single PMU frequency measurement that they get at the point of common coupling. So that's a single broadcast signal. And then they all react to this broadcast signal through some control mechanism. And since they're all connected at a common bus, the aggregate power output is then injected to the grid. So literally the sum of all power injections. So we now want all of these individual controlled devices comprising the DVPP to behave together like a single synchronous machine in terms of the desired input-output behavior. For instance, staying with this example, say you have a single frequency measurement and a power injection on a grid, you may want to do something like a virtual inertial response. So you want a transfer function relating power and frequency that goes like HS plus D, so inertia plus damping. Okay, so this would be a grid following fast frequency response. Later we'll of course, generalize the setup to go to grid forming implementations, spatially distributed, voltage control, and so on. But I think this tutorial example is quite good to start with. And then the task of control design essentially is model matching. You want this entire aggregation of devices to behave like a single desired aggregate transfer function. That is the output being the sum of all the individual power injections and the input being the broadcast signal. Okay, so that's the output, that's the input. And you want this to behave like the desired behavior, so there should also be an HS plus D in between. So you want this model matching to happen while taking into account, of course, that the individual devices are not able to do so. So only collectively they can. So you need to take the device level constraints into account. And you want to be able to online adapt to variable generation inside the DVPP. Okay. Before going into the details, I thought I'll present to you a case study that we did with my colleagues in Sweden, actually before the POSYTYF project already started. And that was with Joachim Berg from the Swedish TSO nowadays. And here's a small model of the Scandinavian power grid, just a 5-bus system consisting of wind generation in the south, and north at the coast, we have hydro generation, those are the blue circles, and some thermal generation. And what we took was a particular ancillary service in Nordic grid called FCRD. That stands for Frequency Containment Reserve After Disturbance. And we took the grid code and translated the grid code into a desired behavior, namely the response in case of a frequency shortfall in terms of power injection should actually look like this particular transfer function. And we really took these numbers by taking the grid code and converting it to a transfer function. So this would be the desired behavior. So there's of course a well-known issue that we talked about, namely hydro generation or hydro actuation via governor non-minimum phase. That is, if you want to provide such a desired response of hydro generation, what will happen if you only look at the blue curves here after a fault, those are all the hydro injections, you first go down a dip, so you have a negative response before the response goes up again. The black curve is the sum of all the hydro generation. So that's doing this. Initially, it has this very slow, sluggish response, actually going down. Whereas the dash curve would be the desired response from the FCRD service as specified by the grid code. As a result of this non-minimum phase hydro issue, you see that the frequency does not follow its desired response as indicated by the dash curve, but you undergo this black response. So that's the center of inertia curves. And in this case, you would encounter under frequency load shedding. Okay, so not very desirable. And as a response, the Swedish TSO suggested the following: let's just augment hydro generation with batteries to provide the fast response right down here when hydro is not active. This works, of course, but I personally consider adding batteries a little bit of cheating. It's not the most economic solution. So is there a better one? And yes, there's. Let's use wind generation, right? And I guess people like Horst in the audience know much more than me about wind generation, but wind has this nice phenomena that if you don't operate at the maximum power point, but slightly derated, then you can initially get some quick power out of the kinetic energy in the turbine. So initially we provide power with the wind turbine, which is this gray curve here. But eventually we need to recharge the turbine, that is, we bring it back up to maximum power point, so then the power consumption is negative. But this is fine because we get this initial quick peak, and then hydro ramps up and can cover sort of this negative power injection, and the overall sum of the two injections is exactly our desired response. Okay, so we can here nicely coordinate both hydro and wind to provide the desired response, while none of the two itself is able to do so. Essentially, what this talk will be about is, how do you do this thing, okay? But this is just a cliffhanger teaser for you to motivate why we're doing what we're doing. Good. So let me get you set up with the problem, and then Verena will take over. So now there's many ways you can set up the problem. You can think about a DVPP as, spatially distributed, both in transmission and distribution, or both of them in multiple areas with grid forming and falling controls and so on. We'll not go through all these variations right now. We start very simple, but then we'll get more complicated towards the end of the talk. So the setup is the following. Namely, the topology is that all of the different devices comprising the DVPP are connected to a common bus bar. Okay, these DVP will consist of controllable devices, such as inverter interface generation, and non-controllable devices, such as the hydro turbine governor system, which just given you cannot alter it, right? And finally, we'll consider, for beginning at least, a grid following signal causality. That means what we do, we measure voltage, so amplitude and frequency, for instance, and we control the power injection. Later, we'll turn this also around. But we keep it simple for now to get us started. So what's the problem setup now is a block diagram. So that's our overall DVPP setup, consisting of controllable and non-controllable devices. The input being a global broadcast signal. Think about a PMU measurement at the point of comp coupling in both frequency and voltage magnitude. The output being the sum of both active and reactive power injections from the non-controllable and controllable devices. The non-controllable are indexed by N, and the controllable ones are indexed by C. So for the non-controllable devices, we cannot alter their closed loop behavior. So it's a fixed control, say for a hydro turbine governor system, and it's just given by a particular transfer function that you cannot alter. Okay, it's just some Ti of S. For the controllable ones, so for instance, converter interface generation, we can actually control these guys and specify what should be the desired input-output behavior. Okay, so for the controllable ones, we can specify the Ti of S. Then, of course, the overall input-output behavior from this input, this output, is then just given by the sum of all the individual transfer functions Ti of S of both the controllable and non-controllable devices. Now we do coordinated model matching. That is, we have this anti-DVPP, and we want it to behave like a desired input-output behavior. Think about, say, inertial response between the frequency measurement and the active power. Okay, so we have a desired specification that is, for instance, a desired transfer function between the power injection and the frequency, another desired transfer function between the voltage and the reactive power. For now, I keep this diagonal, so there's an FP and a VQ control. Later, we'll also briefly touch upon which interesting non-diagonal elements you may consider here. But let's keep it simple for now on. And the aggregation condition is very simple. It says, well, the overall input-output behavior should be equal to the specification, so the sum of all the Ti of S across the non-controllable and controllable devices should be equal to the T desired. Okay? And that's essentially putting the entire problem of DVPP control as a model matching problem. So we need to now find local controllers so that this aggregation condition is satisfied, subject, of course, to all the local device level limitations, because they may be limited in bandwidth, in power, or whatsoever. Okay, and now Verena will tell you how we actually go about solving this problem.
Yeah, welcome also from my side. Florian introduced me already. My name is Verena. I'm a PhD student in his group, and I will now proceed to present you the decentralized control design method. For the remainder of the talk, I will use running case studies to explain you our decentralized control design method. These case studies are performed in the IEEE 9-bus system, where you can see the original setup of the 9-bus system here on the left. We have a hydro unit at bus 1 and 2 thermal-based generators at buses 2 and 3. In a first case study, we will now supplement the hydro unit by a battery energy storage system and a supercapacitor to establish DVPP1, which with the goal to improve the poor frequency response behavior of the hydro unit. In a second case study, we will additionally replace the synchronous generator at bus 3 by a DVPP composed of wind, PV, and a STATCOM battery combination. And this DVPP should provide frequency and voltage control. Also, for DVPP3, we will consider time-varying generation capacities of the weather-dependent devices. One overall comment to all of these, or to these 2 case studies, you might have realized that we are considering batteries within our DVPPs, which is somehow against this original positive spirit. However, our control design in general is able to handle any kind of generation. So we will just use these case studies as examples to demonstrate our control method, whereas in general, we could kind of use any arbitrary kind of device aggregation as long as a generation unit can be represented as a dynamical system. And of course, this is also maybe then also part of other work packages to elaborate on different reasonable device aggregations and setups. So we just took it now as an example. The core of our decentralized control method is a divide and conquer strategy, which consists of 2 steps. That is disaggregation and pooling and the local matching control. We first start to disaggregate the desired transfer function T desired into local desired behaviors for each device. Depending on the resource availability, this disaggregation can also be adaptive. This means that for different instances of time, the disaggregation might look different. In a next step, we then need to design a local matching control for each device to match the desired behavior we have specified before. In the following, I will now go into detail on both of these 2 parts. So to disaggregate our desired DVPP specification, we will use dynamic participation matrices, which are essentially matrix transfer functions composed of sub-transfer functions that are the so-called dynamic participation factors for the FP and the VQ channel. As Florian mentioned before, we start simple for now, considering such a decoupled structure when the DVPP is connected at one bus in the transmission system. Using these participation factors or participation matrices, we can derive the resulting DVPP aggregation condition as follows. That is, we require the sum of all local closed-loop transfer functions to be equal to the sum of all reference models. And those in turn, or this sum in turn, should be equal to the desired transfer function, which is or which can be assured by normalizing the participation matrices, and with this the participation factors, which is described by these participation conditions here. To select the participation factors, we distinguish between the non-controllable and the controllable devices. For the non-controllable devices, this participation factor selection is quite straightforward. We just simply invert the desired transfer function and multiply it with the fixed closed-loop transfer function of these devices. For the controllable devices in turn, we kind of are free to define the participation factors as transfer functions, and we characterize them by a time constant to account for the device-specific bandwidth limitations and a DC gain mu to take the power capacity limitations of the devices into account. And using these 2 parameters, we can now divide the set of controllable devices into 3 categories. That is, we envision a low-pass filter participation behavior for devices that can provide regulation on longer time scales, so also including steady-state contributions. Then we consider a high-pass filter participation behavior for devices that are able to provide regulation on very short time scale. And of course, we also then consider some bandpass filter participation behavior for all the remaining devices to cover more or less the intermediate regime. Coming back to the running case studies, here you can see the magnitude Bode plots of the participation factors for the FP channel in both case studies. On the left, you can see the blue curve here describes the participation factor of the hydro unit, which is, if you remember from what we've said before, kind of a fixed participation factor, which is naturally given by just multiplying the hydro and turbine, the governor and turbine dynamics with the inverse of the desired transfer function. And based on this fixed participation factor here, we can now arbitrarily choose the participation factors for the controllable devices, battery and supercapacitor, which we choose given the physical limitations of these devices as a bandpass filter and a high-pass filter accordingly, such that the sum of all is equal to 1. Yeah, in a very similar fashion, we also choose the participation factors for DVPP3. Here we do only have controllable devices. This means we can choose all participation factors on purpose. So for the wind and the PV, taking their bandwidth limitations and also their generation capacities into account, we choose them as 2 different low-pass filters accordingly with different DC gains. And the StatComp with the battery should behave like a high-pass filter. Next, we need to do the local matching control with the objective to find local matching controllers such that the local closed loop behavior of each device matches the local desired specification, as we have indicated it here. To do so, we consider the following setup for the matching control that consists of the plant dynamics here. So this plant dynamics basically describe the dynamic system of the resource interconnected with a converter to the grid. The other part of our control setup is the matching control, which is composed of the reference model that describes the local behavior and a state feedback controller K. For this control setup, we now consider an augmented system with the state Z that is composed of the state X from the plant, the state XR from the reference model, and the integral of the error, where the error is the output error of the plant and the reference model, as indicated here in the figure. This augmented system is shown here on the bottom right, where the overall closed loop transfer function from input disturbance to error, which is the performance output, is specified as n of s. And now these state feedback controller K here can be obtained by minimizing the matching error in the infinity norm, as indicated here by this sketch of an optimization problem. And just as a side note, we also include some ellipsoidal constraints to take some transient device limitations into account. So far, we have all the ingredients together, what we need for the very simplest case of a DVPP with fixed generation capacities. Yeah, and this is exactly what we have in case study 1. So just as a kind of motivation for DVPP1, which will come in a second, the original system where we have a standalone hydro unit at bus 1 has a very poor frequency response behavior after, for example, a load step or also any other kind of disturbance. I think we have mentioned this example quite a few times now, so, you know, because of this minimum phase behavior. Now, if we supplement the hydro unit by this battery and supercapacitor here to establish DVPP1, we can obtain a much better frequency response behavior, as it is shown here by the gray curve in the top plot. And why do we have this improvement? Of course, if we consider now the active power injection, we can see that this is much larger right after disturbance compared to the initial system with the hydro unit only. And this active power injection is now composed of the different DVPP device contributions, where we can see very nice how the supercapacitor in green has the high-pass filter injection behavior. The battery comes then with a bandpass filter injection behavior. And finally, in blue, we have the original hydro response, which is something like a low-pass filter, more or less. And also, as a side note, by looking at the dashed lines of the two controllable devices, we can nicely see that the matching of the matching controller is quite accurate. To take it now one step further, we can also now take fluctuating power capacity limits into account by our control, and we do this by making it adaptive. In particular, we consider adaptive or time-varying DC gains of the low-pass filters, and we indicate this now here by making this parameter mu time-dependent. And therefore, we also now call them adaptive dynamic participation factors. These DC gains are updated during real-time operation proportionately to the power capacity limit of the devices, which in case of weather-dependent sources can be now time-varying. Of course, to update these participation factors, we need some sort of communication. Maybe just as a side note, the entire control we have presented so far is a fully decentralized control. So each plant had its own local control, and there was no other communication or coordination with others or with some central unity. But to make now this adaptiveness gonna work, we require some communication, which could either be centralized, like it is shown or sketched in the figure on the left, or it can be distributed. In a centralized case, we would think of a DVPP operator that collects the different generation capacities and broadcasts back the desired participation factors or the DC gains. And in the distributed implementation, we would just assume to have some peer-to-peer communication and then some consensus algorithm to compute the DC gains. By making our participation factors adaptive, we also need to slightly modify the matching control, and we do this by resorting to an LPV H-infinity control, which can take these parameter-varying local reference models into account. Coming back to case study 2, to quickly compare or to quickly get an intuition how this adaptation of the participation factor works, we again consider the participation factors for the FP channel. So on the left, you can see the picture. I have already shown you a couple of slides before. During nominal conditions, here we can again see these low-pass and high-pass filter behavior of the individual devices. And now, assuming that, for example, we would have some degrees in PV generation such that it's not available anymore, which could happen during a cloud, then a reasonable adaptation or reschedule of the different participation factors would look like this. So we can see that there is no PV contribution anymore for the DVPP control, but the wind power plant would now need to take over the entire steady state contribution. To also see some of these results now in the time domain frame, let's consider the simulation results of case study 2. So first of all, you remember we replaced the synchronous generator at bus 3 by DVPP3. And by now looking at the frequency and voltage response, you can nicely see how the DVPP more or less provides an adequate replacement by the choice of our T-desired transfer function. We did not on purpose try to mimic the synchronous machine here. We just choose some more or less reasonable behavior a synchronous machine would generally have. If we have now a closer look into the internal DVPP behavior, for example, let's take the active power injections, we can see how the overall active power injection given by the gray curve is kind of established by different individual contributions of the devices. So in green, we have the high-pass filter injection of the STATCOM, and in yellow and blue, we have the low-pass contribution from wind and PV. Again, also the matching is very accurate. By the way, I forgot to say or to mention, in this first scenario here, we considered a load increase at bus 3. Now, we consider a decrease in PV capacity, and on purpose, we choose this decrease to be exactly of the same size like the load increase we had before. So we in this second simulation part, we want to make sure that the active power deficiency is the same, because then we can get some reasonable comparison. And yeah, let's start by looking at the frequency. So we can see how this frequency response looks exactly identical to the one during the load increase, where we had nominal conditions of the devices. And this is assured by the fact that we have, again, exactly the same sum of active power injections of all devices as we had it before. So by comparing the two gray curves, you can see that towards the grid, the DVPP does exactly the same. So it injects exactly the same powers. This also holds for the reactive powers, by the way. But if we now look a bit closer into the internal behavior of the DVPP, we can now see here how there is no PV contribution anymore, but the wind has to take over the entire steady state contribution. And this is exactly what we have seen in the Bode plot before. So the benefit of this setup here is that we have an unchanged overall DVPP behavior during some weather dependent or during some variation of weather dependent sources. Yeah, so far I have shown you our or the basic idea of this very simplistic DVPP setup, where all devices have been connected at one bus and where we have considered a grid following signal causality. In the remainder of the talk, I will now present you some extensions of this original setup and also our ongoing research. First of all, let's start by considering grid forming DVPP control, where we still assume for now that all devices are connected at one bus, we name this bus now the PCC, the point of common coupling. A quick repetition from what we have heard so far. So in case of a grid following DVPP, we were considering that the power injection of the DVPP at the point of common coupling is controlled as a function of the frequency and voltage magnitude measurement. So we had that this T desired here gets as an input the frequency and voltage measurement, and as an output of the DVPP, we have an active and reactive power deviation. Now, if we consider a grid forming signal causality, the inputs and outputs basically switch. This means that now we require that our DVPP imposes the frequency and voltage magnitude at the point of common coupling that is controlled as a function of the active and reactive power measurements at this point of common coupling. In the following, I will now give you some more insights on this grid forming DVPP control strategy, which is of course much more challenging, since obviously we cannot just simply sum up frequencies or voltage magnitudes anymore. So you remember here in the grid following case, we were summing up local active and reactive power contributions of the devices, which is now not possible anymore. Let's start with the frequency control architecture of the grid forming DVPP. Here you can see a feedback interconnection of the local DVPP dynamics and the dynamics of or power flow equations of the DVPP interconnection network, for example, given by the transformers of the devices. As an input, we consider a vector of active power disturbances to the individual DVPP devices. And as an output, we consider the frequency deviations of the devices, exactly. As already mentioned, we have on the one hand this local closed loop behaviors of the individual DVPP devices. And on the other hand, in feedback connection to this DVPP dynamics, we have the linearized power flow equations, which are given or specified via this Laplacian matrix here. As a side note, this Laplacian matrix can be derived from the Cron-reduced setup of the DVPP interconnection network. Here on the bottom, you can see an example with 3 devices, where on the right, we see the Cron-reduced setup of this parallel device interconnection. And now, if the network is tightly connected and purely inductive, for this feedback interconnection, we can derive the coherent response from the input disturbance vector to the output frequency vector by this transfer function here, which is the inverse of the sum of the inverse closed loop transfer functions of the devices. And by multiplying out these vectors of ones with the input vector, and also making the assumption that due to the inductiveness of the interconnection network, the delta P at the point of coupling is more or less the same as the delta P as the local disturbances, we can derive the frequency dynamics at the PCC. And this already looks like a DVPP, right? So yeah, with this, we can therefore derive the aggregation condition, which is now slightly different to the grid following one, and given like this here, where we require the inverse of the sum of the inverse transfer functions to match the desired specification. For the voltage control, we can unfortunately not derive an exact analogy to the frequency control setup, since there is no coherent dynamic behavior of local voltage magnitudes. However, we have an additional setup here where we consider a common input signal given by the voltage magnitude deviation to the devices. And again, by summing up the reactive power injections of the devices, we obtain the aggregate reactive power output of the DVPP. We consider local controllable closed loop behaviors of the devices, and based on them can derive the aggregate DVPP behavior by taking the sum of all closed loop behaviors multiplied with the voltage measurement. And now, by making sure that the reactive power deviation at the PCC is more or less equal to the aggregated reactive power of the devices, we can now formulate the aggregation condition, which means, or which requires, that the sum of all local closed loop transfer functions, and now please be aware of the indices from V to Q, so what you see here from V to Q, should be equal to the inverse of the desired behavior from Q to V. So you remember the original or the initial specification for the grid forming DVPP was from Q to V. And now that we have these two aggregation conditions, we can kind of use the same tools as before, apply the adaptive divide and conquer strategy, the disaggregation, the online adaptation, the model matching, and so on. And to give you also some, or to show you some numerical results, how good this, grid forming DVPP control works, we have, in analogy to the simulations before, a very similar case study. Now we replace the synchronous machine 2 at bus 2 by this DVPP composed of wind, PV, and STATCOM. We define such a decoupled PF and QV control for the DVPP. And if we simulate a load step at bus 2, basically a load increase, it's not a step, it was, I think, a bit smoother, then we can see how the frequency and voltage response matches the desired behavior very accurately. And again, according to the participation factor selection, we can see how the individual devices have a particular contribution in active and reactive power. And also in the grid forming case, we can have adaptiveness. That's not a problem. In analogy to before, we now implement a decrease in wind generation, which causes the exact same active power deficiency as during the load increase. And you can see now again that voltages and frequencies are just coinciding, while internally the DVPP contribution have changed according to the wind decrease. Just to give you a quick idea, a next level, of course, would now be to combine grid forming and grid following devices. I don't want to go into detail too much about this, just to show you like the rough sketch. We are again, for the frequency control, back in the setup of the grid forming DVPP, where we now include these grid following devices here in the diagonal matrix of the local DVPP dynamics. By kind of using a little trick, we consider some fictitious frequency dependent loads and let these frequency dependency factor go to 0, such that we can derive a transfer function from the power injection to the frequency also for the grid following devices, which is essentially just given by the inverse of the actual grid following closed loop transfer function. It's somehow what we can expect. And yeah, with the same principle as before, we can derive the coherent closed loop dynamics, which is now composed of grid forming and grid following transfer functions, and of course then also derive the aggregation condition from this. Also for the voltage control, we can create some hybrid control setup. However, for reasons of time, I will skip this now. And last but not least, I want to give you a quick preview on a spatially distributed DVPP setup. Florian already mentioned it in the beginning. So there are various different implementations or scenarios one could imagine how devices are positioned in the power grid. We kind of try to start with these two cases. One is a transmission system DVPP, where we assume that all DVPP devices are somehow spatially distributed in an area of the transmission grid. And this area has several point of couplings to the rest of the transmission system. And very similarly, we consider a distribution system DVPP, where the devices are spatially distributed within a distribution system that is connected to the transmission system. And in both cases, now the goal or the idea would be to somehow make these areas behave like T desired. The underlying assumptions we need, at least as a starting point, is that we do not allow for any other dynamics in this area that kind of disturb our control design procedure. So we require, or we, at least for the control design, we require constant power loads, and also we require that there are not other devices with some unknown ancillary services provision. So we as the DVPP operator should be aware of the dynamics happening in there, such that we can take everything into account during control design. Yeah, and what we basically do is the following. So in case of the distribution system, as the Rx ratio of the lines is now equal to 1, we do not have decoupled power flows anymore. And therefore, we resort to these rotational powers, which some of you might be familiar with, to decouple the power flow equations. And this is then exactly now where the coupled structure of T desired becomes relevant. Florian mentioned it already in the beginning. And so that in total, like just to give you a quick idea, we can consider for the transmission system DVPP a lossless active power transmission. And for this distribution system DVPP, given this rotational power, a lossless P dash transmission. And since both these two quantities are then lossless, we can kind of still use our, can use the frequency control setup we have already seen for the DVPP at 1 bus. In case of the distribution system, we need to modify it to have a P-F control, which results in a coupled T desired now. So this is very nice to just have basically the same as before. We also observed some limitations of this spatially distributed scenario, and that is we have a lossy Q or Q dash transmission. And therefore, by also thinking carefully how we could somehow establish a DVPP for QV or Q-V control, we realized that, basically we need the full network information within these DVPP areas, and also real-time measurements of almost every node in the system, as well as some centralized coordination to take all these losses into account, which is required to make sure that some sort of T-desired is established. This, however, is a bit unrealistic, especially in a distribution system. We cannot rely on full knowledge of everything. And therefore, our proposed solution would be, in this spatially distributed setup, to only consider a global PF or P-F DVPP control at the point of couplings, and just use some independent local QV and Q-V controllers of the devices. Yeah, that brings me to the conclusion of our talk. We have presented you our DVPP control strategy, where the goal is to control a group of heterogeneous renewables to provide dynamic ancillary services. The keyword of our approach, or of the DVPP concept in general, is heterogeneity. So we use different device characteristics to complement each other. And as already mentioned in the beginning of our talk, one main motivation for such a DVPP is to reduce the need of conventional generation for dynamic ancillary services provision, while being still as reliable as such a synchronous generator. We have presented you an adaptive divide and conquer strategy to address the DVPP problem, which is based on a fully decentralized control method that consists of 2 steps: the disaggregation and the local matching control. In our control strategy, we also incorporate the DVPP internal constraints, and we can extend it to be online adaptive, such that we can also take fluctuating device capacities into account. One minor comment or one side note, we have also, or basically Michael mainly, has also developed an alternative DVPP control design approach, which is based on a centralized optimization problem. So he basically just starts already with a centralized formulation without all these participation factors. So he does not kind of do this disaggregation. He just optimizes over the entire device aggregation to obtain appropriate controls. And yeah, finally, in some extensions and our ongoing research, I've presented you our suggestion for a grid-forming DVPP control strategy and also a hybrid control setup, as well as some first ideas from our side towards to a spatially distributed DVPP, both in the transmission and the distribution grid. Yeah, then I think we are more or less now at the end of our talk. Yeah, so now I guess it's your turn. So if you have questions or if you want to start some discussion, we are now ready here to respond.